Okay, good morning, all. Thanks for being here. If you're able to make the live stream, I appreciate it. This is it. This is the last one. So we won't be meeting next week because the semester will be over. I got the project fours out, and the main reason I was able to do that, well, in addition to me getting up very, very, very early this morning. Happy Monday, Magenta. Hello, Edcast. Nice to see you. Um, anyway, so I got up very early to try to knock out grading. But one of the reasons why I was able to get the grading done before I met with you is because your projects were so good. So thank you for doing that. Then I can move on to projects and other classes and hope that they do the same. Um, although I'm not putting any wagers on it. Okay, so we're doing one last bit of just kind of, I don't know if I think of it as bonus content. This is highly relevant computer science content. Um, but in terms of deliverables in our class, you'll have one last lab. So one last lab, one last discussion, and then your semester is over. Um, so yeah, we're talking about hashing and hash tables today, which if you might sort of go out there and think about where you encounter those letters together, hash, like hashtags in Twitter, and what does that potentially have to do with hashes and hashing algorithms? My guess is that it does have something to do with hashing algorithms. Okay, so anyway, that's what we're talking about today. Is hashing, and then a data structure called a hash table. For us, a very primitive one, just so you can get the concept. And then I'll try to leave you with hopefully some useful thoughts going forward. For those of you who are continuing on, hopefully all of you are continuing on to something beyond this. Okay, so let's walk through the module. So projects done, projects graded. If you want to see the details like I've been doing, I pasted in my rubric with your scores related. So hash tables. So we will implement. We'll also use the standard library array so that you can see how that works. And then we'll use vectors for this thing called a bucket. And then we will make a hashing algorithm to go along with it so that we have a chance to talk about the fundamentals of hashing, which include keys, hashing functions, for us buckets, and then also collision handling. All right, sounds fancier than what it really is. The algorithm we're going to use is actually fairly basic. I'm set up, by the way. I thought I wasn't going to draw pictures for you anymore, but I am going to draw one more set of pictures, so sorry about that. I know my pictures are awful. Let me open up the lab repo, and I'll come back to it. Actually, let me get doc test open too. Let's see. So the discussion is just kind of a farewell, and hopefully everyone does well, but just one last thing. And I would like people to think and share your thoughts about how you would continue to grow your skill set. For those of us in computer science, and for many other disciplines for that matter, many of the sciences, and mathematics, they use programming a lot as one of the tools that they use to explore their ideas, express their solutions. So getting better at it is a valuable thing to do. So anyway, I'll throw some ideas out there to you before we leave today, and then hopefully in your discussion, we'll have some interesting ideas about what people see as a way to keep moving forward. It's not like riding a bike, at least not in my opinion, programming. So it's something that you have to sort of work on. Even if you don't consider it to be your primary interest in computer science, it is still one of the principal tools that we have that we use to explore and express our ideas. Okay, anyway. Robo, nice to see you again. Robo has to see me a lot on Mondays. And then reminders. So we do have one last lab, one last discussion. For a lot of you, your score is already made, so you can choose to do or not do the lab. For me, it's Um, a little bit less grading if you don't, but I hope that you do the lab so that you have that sort of hands-on experience in the code that is doing some primitive hashing, and then a primitive application of a hash table. All right, there's those things. So do I want to draw a picture first? I think I am going to go ahead and draw the picture part first, and we'll go from there. So make sure, I need to bend the camera a little bit. Okay, so we're talking about hashing and the hash tables. So a hash table is really just an array. That's all that it is. I'm going to go ahead and put some index values here. I guess technically you could use many other data structures, but for us, let's just think of, when I say hash table, we're really talking about an array with a particular set of algorithms applied to it. So when we're talking about hashing and hash tables, the whole point of this is to try to get the most performance out of something like an array that you can. The reason why arrays are awesome is because if you have the array name and the desired index, the computer can very, very, very quickly get to that spot in memory. So arrays are super fast. They are super performant. So they are very good, if you are clever, for storing data. The catch that we've been trying to work ourselves around all semester is that they have a limited size. So they are easily the fastest data structure that we can use, so we love them for that. But they have this limitation that they are fixed in size, and that's a problem. The other limitation is if we had, say, an array of some kind of an object, how do we know which element goes at which index? So the question here I'm writing is, how do we know that a specific item that I want to put in this array goes at this specific index? How do I know that? And the way I know that is with a hash or a hashing algorithm. Now we're doing kind of the thumbnail sketch of this because I know we're at the end of the semester for you guys. But the algorithm that we use to figure out which specific location in an array, in a hash table, a specific object should go is called its hash, or you might think of it as a hashing algorithm. So that's the whole trick. And you can think about this, just think about it like a classroom that you go to. And your classroom is like an array of seats. And your teacher wants you to sit in the same seat every time. So they have to pick one of those seats for you. The hashing algorithm that we would often use in a case like that would be to alphabetize people by first or last names. Where there are collisions, like there's two people with the last name Jones or Smith, for example, we'd probably have, we would have some algorithm in our classroom model to resolve that collision. So if we have two Smiths, then we might say, okay, well, your last names collide, so what are your first names? And if their first names collide, then we go to their middle names, maybe their birthdays. But that's actually hashing. That's how do I take this person who is a combination of information that I can use and place them in a specific location in this fixed size classroom. So the hash is the way that we decide which specific index the person shall be located. Hopefully that makes some kind of sense. Just as a real world example. So of course we do things a lot more abstractly than that. We usually have some kind of object. We could use like the food item that I talked about last week. So if I wanted to find a location quickly in an array for a food item, I would need to figure out some hash for it that gave me the specific location that it should go into. And because the array is in the computer and the object and the hash are all in the computer, we can't just kind of think this through. We have to express it as an algorithm. So that may not be helpful for anyone. But basically, if we have a fixed set of locations, we have things that we would want to, objects that we would want to place at specific locations without overlapping them or colliding them. How do we figure out an algorithm based on the given information about that object that would allow us to place it in the same specific location every time? That's kind of what this whole problem of hashing is about. So I'm going to do a little bit of back and forth, but for us, we're going to use an array as a hash table because they're fast. So if we can figure out a way to take an object, get an index for it, then we can take advantage of how fast arrays are to place that object at its given location. So let me do an example of a bad hashing algorithm. Actually, kind of a worst hashing algorithm. And then we'll go do a slightly less terrible than the worst. Okay, so let's start a REPL and let's do a bad one. Like a really bad one. Oh, darn it. Just give me C++. There we go. And I'm going to use a C++ array for this. So I'm going to include. So while I'm on it, by the way, there are primitive arrays in C++, which is probably what you're used to. And there are standard template library arrays, which is what we're about to use right now. Which is what I always use anymore when I want an array. But anyway, we're using the standard library array, which is a little bit different and in some ways better than the primitive array that has a very limited feature set. So for example, a primitive array that you may have used doesn't know its size in C++, but a library, a standard library array, actually does know its size by calling a function. So let's do just let's start just with an array for strings as an example. So I'm going to make an array. I'm going to need to include string up here. So the template for the standard library array in C++ is what you're storing in the array and how big you want it to be. And I'll just call it, I'll call it my hash table. Okay, so here's the trick. If I want to say, where should I place the string lemon in the hash table? Kind of like where should I seat the student in the class? Where should I place the string lemon in the hash table? So I need a hashing algorithm that, one, gives me index into my hash table, which would be index values 0 to 9. Two, what else do I need? The other thing I need for my hashing algorithm, a hashing algorithm that actually gives me a location in my hash table, not outside of the index values 0 to 9. The other thing that I need, though, is that I need lemon to hash to the same location every time. If my hashing algorithm doesn't give me the same location every time, then it's not a hashing algorithm, basically. It's just a random number locator thing. So a hashing algorithm needs to give me an index into the data structure I want to work with, which in this case is my array called hash table. And then the hashing algorithm needs to give me the same index for the same values every time. Okay, so I'm going to be not clever about it. So I need something that basically converts the string lemon into an integer between 0 and 9. So how do we do such things? That's what hashing algorithms are. So I'm actually going to make a function for this. So it's going to return me an unsigned int hash. I'm going to give it a string, and it's going to return me a hash value, which would be an index value. I'm going to go with the most easiest of things, which is to simply take the size of the string. So lemon would be a size 5 string. So this hashing algorithm, which is simply using the size of the string, it works because it gives me a value between 0 and 9. So lemon being a size 5 is going to go into the array at index 5 every time. And lemon will always be size 5. So my hashing algorithm guarantees that I always get position 5 for lemon. And it would simply work like this. We would say hash table, and then as the index, we are going to hash lemon. So the locator, the where to seat lemon in my hash table, is what I get by hashing that same thing with my hash algorithm. So it should go in index 5, but let's go ahead and make sure that that's true. So I'm going to do a, I guess I'll do one of these guys. So here's one of the things we love about standard library arrays, that it has a size. And then I'm going to do, I'll put out the value. Just so we can see if lemon went into the same place. Oh, I'm over. Okay, so I don't know if you can see this, but I'm getting a complaint because I am shadowing the standard library hash algorithm. So I'm going to have to differentiate. So I'll just call it m hash, like my hash. And then I'll use my hash instead of the standard library hash to get around that collision there. Okay, so there is lemon at 5. That's a good thing. I can hash table like if I want to put orange in there, then I can use the same hashing algorithm to locate the spot for orange and then place it in the array. So I'm hashing into a hash table. My hashing algorithm still works okay because orange always goes in position 6 because its size. Lemon always goes in position 5 because of its size. So the hashing algorithm right now satisfies both of those conditions. It gives me a value between 0 and 9, and it gives me the same index for the same hashing value each time. All right, so, and if we wanted to get it back later, we could say, you know, get me orange. So if I wanted to get orange, then I can go back later and I can hash it to access it. So it's this indexing quickly into a data structure like this is just why we like hashing, because it gives us good speed for placing and recalling data in a data structure. Right, so I'm proving there at the end that I can use the same hash on orange to get orange out later. So I don't know if anyone, we'll see what people think in chat. So Does anyone see a shortcoming to my hashing algorithm right now? I kind of told you up front it is very bad. It is primitive and crude and actually just a very bad one. Nice. So RoboGenko asks in chat, what happens if we have two words with the same amount of letters? So what happens, and I'll ask it here because it's exactly what I was going for. So what happens if I want to place Apple in the hash table? So this is what Robo is asking in chat. What would happen if I want to place Apple in the hash table? So that's exactly the right question, Robo. Thank you for that. So what happens if I try to place Apple in my hash table? I have what's called a collision in hashing terms. So the hash for Apple is the same as the hash for lemon, and I have a collision. And this cannot be allowed to stay this way. So we must resolve this collision. So we can't do this because if I try to hash Apple into my hash table, I'm going to eliminate Apple. Lemon. I will overwrite it, and I don't want to lose data in this hashing. So we have a collision. That's the term that we use in hashing when we have two values that hash to the same index. That's a collision. And we call it resolving the collision when we figure out how do we do that. So we have two techniques. Let's look at technique one first. And try a better hashing algorithm. So let's try a better hashing algorithm and see if we get any luck. So we still have the problem that we have to produce a value between 0 and 9. So we need to get something that gives us numbers, basically. So this first hash is just terrible. So let's try a different one. And see if we can't make it better. So if we're thinking about what we have with the string that might help us out, one thing we could do is we could just hash the first. Well, no, let's try hashing the first letter. Let's say, and see what happens. So let's hash the first letter and see if that helps our situation. So we're going to return .at 0, which is a character, but we can treat it like an integer because in C++ characters are their ASCII values. And I'm going to print this just as an example so you can see. So let's try hashing just on the first character. And before we actually hash it into our data structure, let's just look at what the hashes would be. So we'll do Apple, and we're just going to look at the hashing values. So let's see what hashing values we get from Apple and lemon. And orange. So we're not going to worry about placing it, writing into the hash table. We just want to see. So Apple, if I treat it like an integer, is 97. This is the ASCII, ASCII value. Here, I'll do it on the, I'll do it right here. So if you do ASCII table, you will get this table that shows you the decimals that go with different characters. So the little a over here, if I can highlight that row, I can't. The little a is the decimal value 97. So in C++, calling something a character will cause it to print out as a character, but internally you can actually do math on it and it will treat it as its decimal ASCII value. So little a is 97. So I am getting 3 distinct values. Now what's the problem with these values? I get 97, 108, and 111, so that part's good. I get different hashing values off of them, but what's the problem in terms of my original specification up here? So why are 97, 108, and 111 unacceptable in that state for my hashing? They aren't between 0 and 9. That's exactly right. So they aren't between 0 and 9, and that's a huge problem. So you're exactly right also. So Robo in chat points out that these need to be between 0 or 9, or it's a deal breaker. Robo is also pointing out that as soon as I try to hash lime or apricot, it's pretty easy for me to get yet more collisions. Okay, so let's number these. Let's call it hash. I'll start at 0 and I'll call this hash 1. So let's deal first with the fact that they're in the wrong range. So I need to be between 0 and 9, and I don't know, does anyone know what I can do here to kind of scrape off or filter off a value and guarantee that I only get between 0 and 9? It's a little trick we can use for this. So how do I take an integer like 97 and guarantee that it is at most 9? It's a harder one. Let me do my fix my hashes first. And these are going to be hash 2s. Okay, so let me show you the other trick here, which is very handy for hashing. So if I know, we can do something like substring and just take the first digit. That's not a bad idea, Robo. That actually might be something to try. Like convert this back into a string and then take the first digit, which would work. Another way to do it, which is what we'd often do. Often what we'll do is we'll specify a maximum, and then we'll use this little trick of arithmetic. So if you mod by 10, for an example, you can only get the values 0 through 9, because as soon as you evenly divide by 10, you get 0, and then you can get remainders anywhere from 1 to 9, and then back around to 0. So often what we'll do to get these hashes down into the desired range is we'll use the mod operator, and this is really the, if we say the maximum value, then we need to mod one above that maximum value for this to work. So let's try it by calling our newly updated hash 1 that now has the max possible. So when I hash 2, I'll say, well, in fact, you know what? So I'm not going to take the, I'm just going to do max. And I'm going to programmatically get the size of my hash table, which kind of then I can make adjustments to the hash table and not have to worry about this call to the function or the function itself. It's just going to assume that the max is exclusive, meaning I'll even put a note here, meaning it's one above. All right, anyway, let's see what we get for hashing values there. M hash 1. Oh, I called it M hash 0 because I'm a dummy. Well, I'll just switch these out. And then I think it'll match what I used it for later. There we go. Okay, so this one is a little bit better. I get 7, 8, and 1, but Robo already pointed out that it would be very easy for me to create new collisions because my algorithm is so crude. What was the other? Oh, line. So anyway, the hashing algorithm is still pretty crude because it still yields collisions pretty darn easily. So that one's not the best. Let's mark it off though. Let's do a try number 3, and let's make it just a little bit more sophisticated. I don't know, but Robo, yours is a good idea, and if we have time, I'm going to try it. But let me just show you. But this Robo had a good idea. Take the ASCII value, although it turns out that notice like the lower letters, you get a lot of ones in there. So you can imagine the collisions are going to come pretty quick there as well. So let's try another hashing algorithm here. So hopefully everyone's kind of following. We need to somehow take a string and turn it into a number that's an index between 0 and 9. So our first try was simply hashing by the lengths and then putting them in the array. But then I quickly realized, of course, that the lengths is gonna yield a lot of collisions. So then I tried another approach, which is to use the letters themselves and get their ASCII values, and then use mod to sort of carve those values down to the desired range that would fit inside of my hash table. But still, we noticed, and Robo noticed in chat before I got to it, that it's pretty easy to cause a collision that way. So let's see if maybe working with more data might help. So here's let's try a different approach. So a different approach might look like this. I'll call it in. We might do this. So for char C in the string S, n plus equals C. So here I'm doing again, I'm using the character, but for its ASCII value, which C++ can seamlessly do. So I'm basically just summing up all the values. And let's just see what the summed up values look like. So if I work maybe with all of the character data and sum them all up, maybe I get something a little bit more unique looking. So let's try out hash 3 on these things and see if we get, if we do any better. All right, so we're going to use hash 3 this time, and let's see what those look like. Okay, so the numbers are all unique, but I have this issue again where they're too big, so let's carve them down. So I'm going to return n modded by the max, and again, max is exclusive, not inclusive. And let's see if we do any better this time. So we did better. We did a lot better, in fact. We have no collisions in that first round based on this slightly making more use of more of the data. But I'm pretty sure that if we try hard enough, let's get some other Let's try some more and see if we get any more collisions. So I'm just going to duplicate all that, and then, so banana. And if anyone's out there in chat, if you could help me with some fruit names, I'd appreciate it. Cherry. I'm doing okay, actually. Now I'm in trouble. Strawberry. Grapes. Thank you, Magenta. That's good. Grapes. Grapes. And then I got to do one more. Oh, gotta. Kiwi. I already got kiwi. Probably melons. Okay. Let's do, yeah, we'll just say melon. All right, so we're going to try out our hashing algorithm, our version 3, where we sum up all of the ASCII values and then carve them down to the desired range with the mod. And let's see if we're doing any better. 0, 9, 6, 4, 3, 9, 6, 3, and 4. We got... so once we expanded the data set a little bit, it was starting to already get some collisions. So as far as I am aware, there is no perfect hashing algorithm in the universe. There are always going to be collisions of some sort. So it's good to have a better hashing algorithm because you would rather not have to deal with collisions if you don't have to. Another way to resolve, we can try a better hashing algorithm. We can try a secondary hashing algorithm. So if the first hashing algorithm yields a collision, we could try a secondary hashing algorithm to try to get around the collision, and then a tertiary algorithm, and so on. But there's likely no perfect hash. So we need some way to not lose data on a collision. And this is where buckets come into play. So one way to deal with collisions is to use what are called buckets. And basically, and I'm going to draw a picture now, and this I think is the end of my picture drawing work today, although I got to do some tomorrow, I think. So let me switch over and draw you one more picture. We're doing good on time. So, okay. So hopefully everyone kind of gets the basic idea of this hashing thing. We have some piece of data. We were doing strings, but we could have something more complex, which we'll look at in the lab. And we have some piece of data that we have to figure out some algorithm that gives us a unique index integer for that piece of data that can then be used to place that data. So the data and its index, right? That's what tells us where to put it in the hash table. But then we've seen for the very primitive hashing algorithms, pretty bad for avoiding collisions. You can do slightly better by maybe using more of the data, which we got a little bit better by summing up the ASCII values and carving them with a mod. But we still ended up pretty quickly with lots of collisions. So another way of dealing with collisions is simply to accept that they're going to happen and then alter your data structure to allow for that. So the technique is called buckets. So the technique is that instead of having a single item at an index, we have sort of a bucket for items at that index. So every time an item hashes to an index, it doesn't go over the top of that index. It goes into the bucket at that index, which I'm going to implement twice. I'm going to go do it with our little fruit example, and then we'll do a slightly prettier one here in just a moment. So we do have this option, which is a common approach, I believe. We just we have the array with its indexes, but at each location, we don't have a single item. We have a bucket for items. Nice one, Magenta, like a vector. Yes, exactly. So Magenta is actually already picked out my preferred solution, which is to put a vector there. So let's go do that in code and give ourselves a bucket. So we're going to change this array right here. We're going to put, instead of storing the strings here, we're going to store vectors of strings. I'm going to put some spaces so you can see this a little bit better. So each array position is actually an expandable vector. So now it can absorb these collisions better. That's a bucket. Let me give myself an include for that. And now let's go use it. I need to get rid of all of this stuff no longer works anymore. So I'm just going to comment that out. In fact, let's just, no, I'll just comment it out. Okay, so how do we work with this bucket? So let's comment out all of these hash try 2s, all of these hash try 3s, and let's use our bucket. So now you have to think in 2 dimensions, because if I go to a particular location in my hash table, I don't get a string anymore. I get a vector of strings, which is another collection. So here's what that would look like. So if I were to go to my hash table, and I'm going to, at the index, so my hashing algorithm will take me to the right bucket now. So I'm going to use hashing algorithm 3. It's going to be for lemon, and then the size of the hash table itself. So that is a vector. That whole thing is a vector. That's the bucket. And I can take a vector and I can add things onto the back of it. That's how I would get lemon into the bucket that is at this location in the array. Looks a little bit scary, but that's what's going on. Let's put more. 4, 5, 6, 7, 8, 9, 10. This is going to be no fun. Lime, kiwi, grape, cherry, banana, now I have, oh wait, they're just right above. Why don't I just look above? Apricot, apple, lemon, orange, forgot orange. And then make sure these carry across. So remember, I use what I want to put in it to get the hash, which is the index, to a bucket. And then I put what I wanted. So I hash and place the same thing, right? I hash orange for that index, and then I place orange at its hashed index. Let me make sure all these get carried across, lest I get something that looks stupid. Almost there. Okay, so in theory, I have some collisions going on, but the collisions have now been resolved by using buckets at these locations. So now let's do the slightly scarier thing, which is how do I see what is going on in there? So I have an array, and then as I stop at each array, I have to loop through a bucket. So it's 2 loops. I have to loop through the array first. If I loop the array, I'm looping to get the buckets, which I will call them buckets. So as I loop the hash table, I am getting vectors of strings, which are my buckets. Once I have a bucket, I can loop through the bucket and get the strings inside. And then let's, well, let me give myself a, and I want an index so that for each bucket I can print out its index value as well. So do this old trick. Okay, so it's not as bad as it looks, but I have to go through the hash table to get the buckets. And then once I have a bucket, I can go through the bucket and get the strings. And then I didn't print the string with the space after it. So now we should be able to see the full contents of the hash table with each bucket at its index value if I did it right. So let's see what we got here. So I forgot to increment the I. Okay, so here's my hash table. So obviously there were several collisions, but I didn't lose data. I just opted to use buckets to resolve those collisions. So hopefully everyone kind of gets the basics here. We like the performance of arrays. So if we can figure out a way to take our complex data and map it down into array quickly, that's hashing, then we can get all that performance out of the array, assuming that our hashing algorithm isn't a bad, inefficient one. But then we've seen that the various ways, just with strings that we've kind of experimented on, how do I get a better hashing algorithm going? And we get these things called collisions, which is when you have two items or more that hash to the same location. So we could have tried to make better hashing algorithms and probably could have found ways to get better hashing algorithms to reduce the number of hashing collisions. But as far as I know, there aren't any perfect ones. So you still have to have some way of resolving a collision that your hashing algorithms will not solve. In this case, we did it by placing a bucket at every location. Anyway, so there we go. Apple hashed in there by itself, but notice lime and cherry didn't. Anyway, so that's the basic concept. I'll share the link. I don't know if anyone wants to see it, but I'll share it. So you can see it, and then let's go see what the lab holds in store for us. So I'm going to make myself a new REPL. If I didn't switch over, I'm going to be upset. Okay. So let me create another one. So CSCI 21, lab 17, and let me go get set up with the code that we've been provided. So I've kind of already shown you much of what the lab already does, but I'm going to go ahead and walk us through it so that your last week is less stressful, I hope, and you can think more about what's going on and then not, and less how to make it go on. Get doc test in here. And then the lab itself. All right, so I need the lab code. I need, is that doc test? Yeah. I need the hash table header. So hash table.h. And then hash table.cpp, which probably contains nothing. Yeah, just this thing. Just as a reminder that that's what I'm supposed to do. Okay, before I do the lab, I'll just, I didn't sort of lay the groundwork of why do we care about speed? Why do we care about the speed of storing and retrieving things? More than ever do we care about this. If you think about the world of social media, how does Facebook or Twitter get a feed to you of the things that it has decided that it wants you to see? So how does it access these masses of information so quickly? it's not just hashing, but basically in computer science, we put a lot of work into speeding up our storages and retrievals of data because we deal with a huge amount of data all the time, very fast. So we're constantly working at trying to figure out how can we store more data but still access it quickly. So anyway, hashing is one of those techniques that we use to try to get faster and better at storing and retrieving data. So it's a big deal. Oh yeah, this had this in it. So the main is just the unit test. I'm gonna run it and see if it even runs. Okay, it does not run. So one of the things that I like to do when I'm handed a unit test, why is there nothing in here? Presumably because I didn't put anything in there. Anyway, it won't run still, will it? Maybe, maybe not. Okay, it won't. But anyway, one of the things I try to do when I'm given code with a unit test attached is try to get it into a building and running state as fast as possible. Which usually means I'm going to have to stub some things out. So we have a struct here called item. It doesn't look like I have to worry about that tons just yet, but let's get all these functions. There's a private one, and then I'm going to clean up all that trash. So I'm going to get it in a compiling state first. Is that everybody? Yeah, I don't need that thing, do I? But was there a private hashing routine down there? There is. I knew I saw something down here. All right, so let's get it building real quick. The class is called hash table. So I'll use that to do some scope resolution. And then I'll set up some stubs here. So void returning stubs, you can just leave them empty. Bool returning stubs needs to return something. I'll return false. This one returns unsigned int, so I'll return 0. This one returns unsigned int, so I'll return 0. And then this one returns a string, so I will return an empty string. And then this one also returns an unsigned int, so I will return 0. I'm trying to get it to where it builds and runs, even though I know I'm going to fail most, if not all, of the unit tests. Still crashing somewhere. Oh, I've seen this. Some of you guys have had this junk before. Undefined reference to hash table get item. Did I miss something? There's get item. Oh my goodness, well, clearly that's not there. I'm missing some stuff. Insert, remove. Where did get item go? I guess I accidentally deleted it. This one returns a pointer, so we can always return a null on that. That might cause a crash somewhere in the unit test, but let's just see if we can get it to where we're building. I know doc test takes forever to build. All right, so it's building, crashing somewhere, but that's fine. It does something. It gets through. I actually passed 3 assertions. But as expected, I mean, anyway, I'm closer now. I've got something to work with. I can start working on the problem of implementing this thing. So it's very similar to what we've just been doing with one little extra wrinkle is that instead of just strings that go into our hash table, it is items. So we have to do something to convert this item, as it were, to hash it into an appropriate sized index. Okay, so let's keep that in mind. So we'll be inserting items. So our hash algorithm is going to have to contend with that item somehow. Remove based on some target contents, which means we're going to have to map the contents to something about the item. What's the items field called? The item has a contents. So when we see these strings for remove, we mean match the parameter string to the item in the hash table string. Get item, same thing. Match the parameter string to the item in the hash table string. The number of items currently stored, not just the number of buckets, but the number of items. We have a hashing algorithm here. Uses the private hash function on the item's contents. Oh, I see. So we have a public hash. The reason why this hash is public, by the way, is because we need people in the outside world who are using our library to be able to hash for retrieval. So we won't show them our hashing algorithm. We'll just say, if you call our public hash with an item, we will return to you the result of our own secret hashing algorithm. All right, and then we have an array with buckets for items of size 5. So it's a very small hash table. And then it's a string, which does some nasty stuff, shows how many items, and then item index, and then tab character needs to go in there, and then each item is actually numbered, which is interesting. Okay, so let's just start working on it and see where we get. Hashing. We already know. Did it describe it? Sorry to go back. Compute a key by summing. Okay, it tells us the hashing algorithm. It's the one that we just did. Sum the ASCII values of the characters in a string and mod them to fit the size of our array. Okay. So that's the same one that we just used. So we will have an unsigned int n. We will take that string. So for charge C in the provided string, this parameter, I'll say this as a parting thought kind of for the semester as well. Generally, you want to keep your functions working only with their parameters. I gave us a little break here where I didn't do that entirely, even though I should have. Anyway, so just pay attention when we're dealing with the parameters. So I'm supposed to be summing the characters of the parameter string S, which is why I'm range looping the parameter string yes, and then gathering up all of the sum, and then I will return that modded by, and then I'll use the items, the size of the items that is our hash table, not the buckets, but the hash table, the array itself. So instead of parameterizing that, I just use the members, the array member items, its size. Same algorithm though, right? Just sliced down to fit. All right, so there's that one. Let's see if we do any better. We did worse, actually. Oh, because I'm not taking the characters from the string, summing the character ASCII values, not the string. Doc test take a while. Okay, so I'm passing 3. Is that the same? I think maybe it was only passing 2 before. I still do crash, but some things are starting to happen. So there's the hashing algorithm. It's a crude one. But it is what the documentation told us to do, which is hash it as a sum of the characters in the parameter string modded by the size of our hash table to get a good index value. Now we can go up. Where's the other hash? So this other hash is simply returning contents, right? So here I'm just showing you that, and I wanted you to see it. We're not going to hash the entire item, which is really just a count and a string inside, kind of like that word class we used on Project 4. We're going to use our private hashing function on the contents string of the item, and that's what the private hashing function expects, is a string to hash against. So our item hashing function is really just cheating and hashing the content string inside of it. I may not keep click and run like this because it's taken a while. But let's see if we pass any more than 3 for the effort. We passed 7 now for getting the hashing working. So I am jumping around a little bit. I did, there's both of the hashes that I did. So I did the private version, which hashes on a string, and the public version, which passes the content string of an item to the private hashing function. Let's see, let's do some of the easier ones, like insert. So not too bad, because basically what we have to do is we go to the items. We're going to index it by hashing the item, which we know actually causes the private string hashing function to execute. That's a bucket, so it's a vector, so we will push back the item onto that bucket. So inserting into the hash table, let's see if there's any notes about preventing duplicates. Yes, do not insert duplicates. All right, so what we'll have to do is oh wait, is there something we're supposed to do? If increment the count if it's already there. Well, we've done this with the binary search tree, so we don't have it operational yet, but we have a get item function, so we can star p to an item equals this get item, and then we're going to have to use the contents of that item because the get wants to know what the contents are. And then we can say if the pointer is null, then it is not already present, and we will add it. Otherwise, we need to take that pointer and increment its count. So there's the insert routine, I think. I'm going to go back and read the documentation here in just a second. So I'm going to try to get the item. As much as possible, I try to use my other functions to make my work a little simpler. So I have not implemented get item, but assuming that I had, I can get a pointer to an item of a specified contents and then see if it's there or not. If it's not there, I will put it in the bucket. If it is there, I will increment its count. I need to go see if that's how item works. So do I just increment the count on item, or is there a function for that? So yeah, it's a struct and a count, so I'll just increment it directly. All right, so there's the insert. I'll go ahead and run it and see if anything happens. Still passing only 7, so that didn't improve my outcomes just yet. So let's do get item. Remove is probably going to be difficult, and then we'll do size, and then we'll do remove. So let's do get item. So let me go read what it says I'm supposed to do with get item. Return a pointer to an item in the hash table by contents. Return null if no item matches the contents. Fair enough. So I have to remember that I have to go into the buckets to do this, which means that I have to go through the hash table first. So I'm going to loop through the items, which is the hash table, getting the item buckets. And then I have to loop through the buckets, so 4. We'll see if this works. I have a feeling I might have to do a little bit of gymnastics here. What are we going to get as we go through the bucket? We are going to get items. And, well, let's just see if it works this way. So we'll get items as we go through the bucket. There's a whole bunch of items in there. If that item's contents are the same as the contents I'm looking for, this thing right here, then I shall return not the item, but a pointer to it. So I have to convert the item into a pointer, and then I'm wondering if that's actually going to work or not. Well, we'll find out, and then we'll make an adjustment. Okay, so if I find an item in the bucket whose contents are what I'm looking for from the parameter, then I will return not the item, but a pointer to it, because that's what I'm told here. Now, if I should get all the way through the hash table and all of the buckets inside, and I still haven't managed to fire off that return statement, then I failed to find a match. I need to return a null pointer. So let's see if what that does. I have a feeling that I'm going to have to head off. All right, I'm passing 13. All right, I know I'm not doing the toString stuff yet. So is it just the toString stuff? Oh, I didn't do remove yet. So there's a possible bug here. I'm going to put a note. The question is, does that ampersand I down there on line 22 now actually allowing us to update the item that's inside the bucket? We won't know that for sure until we start running the print routine. So let's do the size. So the size has to be calculated because it is a combination of the sizes of all the buckets. So I have to go through the hash table. And then I have to get the size of each bucket. So the size is going to be the sizes of each bucket summed all together. So how many items are in each bucket summed together, and then I can return the size. Is it going to gripe at me about that word size? We'll find out. I was passing 13 a moment ago. Still only passing 13, but I got a bunch of removes. Okay, there's a size 9 that's failing. That's because it's expecting to do a remove. Okay, so now we'll go do remove. We still have toString to deal with, and we still have the potential bug here in get item. Are we able to update the item that's inside the bucket? Because I'm pretty sure it's being used for that somewhere. In fact, I know it's being used for that somewhere because I used it for that in my insert function. So let's do a remove. This one is a nasty one. We have to look through the buckets for an item. So in this case, I do know that we need this reference here. So the reason why I am looping to get references is because I need to alter one of the buckets. This is the question I have about get item as well. Do I need this to alter the bucket? So if I take the ampersand out, I don't actually have the ability to alter the bucket in place. But if I use the ampersand, then I can make alterations to the bucket as I loop through. So now I'm going to look for the contents that I want. And I'm going to use the other kind of loop this time. And the reason is because I'm going to use that I for my removal algorithm. So what I'm looking for, so if I look in the bucket at that location and I find contents on that item that match the contents I want to remove, this stuff, then I want to get rid of it. And the way you do that is you do bucket dot erase. It's a vector. You may not remember this part, but basically you can go to the beginning and then offset by that index value that I was using. So this is how I can remove an item from a bucket, in which case I have succeeded. I can say, yes, I removed it. Now, if I get through the entire hash table and all of the buckets and I never fired off that return, that means I failed to find a match. So that's one of the more difficult ones, although probably in listening to me describe it, it made mostly sense. Got to use the hash table to get the buckets. So now I grab a bucket, I look through the bucket for a match, and when I find a match, should I find a match for the contents. So bucket at I is an item, dot contents is the contents inside that item. So anyway, if I find contents at that location that match what I'm looking for, then I want to erase that location. Let's see if I pass any more than whatever I was passing, 14 or 17 or something. I'm getting all the way down. Okay, so Magenta asks a good question. What does that erase operate on? So this erase erases one thing. You can actually use erase to erase a range of things, but the way I'm using erase here is I'm saying from the beginning, offset to that index and erase that one thing. So the way I'm using erase is erase that one thing. You can actually put a comma in here and specify a range of things to erase. But if you just have one argument, that it is that one specific thing out of the bucket. So the bucket is otherwise still intact, and everything else is still there except for that one item that I just erased. I'm now passing, by the way, 25 things, and then we will see how we do it to string. Don't forget that we still have the potential bug in get item. I don't know if get item is actually allowing the editing to take place, but we're about to find out because we're going to string the thing. So now it's time to do a toString, which means we want one of these things. And then I got to go get the template. So square brackets. So items in hash table, colon, the size, new line. Where to go? Oh, it's over here. Wait. I already forgot. Why don't I just take this with me? I'll take this one with me. This one's more helpful. Okay, gotta do something like this. Use an inline marker there if I want. Now I'm going to have to loop. So now I have to loop through, get all the buckets from the items. All right, so, I need, I'm going to, because I need this index value, I'm going to use the other style of loop here. size ti equals 0, I less than this items size. So not the whole size. This size is how many total items, which I have a function to compute that. But for this loop, I need to loop through the items to get the buckets inside. I++. Okay. So now, why did I do that? Oh yeah, because I need this. And then close, and then it says a tab, which is a backspace, /T. And then, so now I have to loop the bucket. So for, I think I can just go get the item. I can. So in this case, I can get the individual items off of the bucket, which is this items I. So I use the other kind of loop, so the bucket access looks a little bit different because I'm just doing an array index. All right, so I've got the header, how many items, and I use the function that I wrote to compute that because I don't know by the hash table size. I have to go count the individual buckets, which is what the size function does. And then I'm using this style of for loop through the hash table, which is this items, because I want to be able to produce that little index per this setup here. So that gives me this index, and then I go ahead and use that index to get the bucket and then grab the items from the bucket. And then what I'm supposed to do here is, for the output, I'm supposed to get the contents, and then a space, and then a parenthesis, and then the count, and then close parenthesis. My guess is followed by a space. We'll find out from the unit test. And then since I'm supposed to do a whole list of them, after I get all the items, I better put another new line here. And let's just see how close we get. I'm failing too. Okay, so I can already see. So if we look at this one, what it expected was, so I got the items in hash table part right. Oh, look, these are supposed to be tabs. Is there a tab down here? I don't know. So I'm supposed to put tabs in between them, apparently. Or I guess I should go read the documentation. But one thing I'm noticing is that this is what was expected, and there's counters in there that I don't match. So my get item code is wrong. So I need to go fix that and see if that helps the counters, and then we'll deal with the what I should have done, which is read this. Note, insert a tab character after there and output item contents into a field width of 10. That's why. Okay. Item contents goes into a field width of 10. I can fix that quickly. So I'm going to take this space off right here, and I'm going to put a field width of 10 right there. So it says output the output the contents into a field width of 10, and it tells me to use this function set width, which basically creates a little invisible column of 10 characters, and then contents is placed inside of that column. Right justified, or right aligned by default. The other thing I noticed, though, is that the counters weren't helping. So my suspected bug is, in fact, a bug. Is &I letting us get into the original bucket? It is not. How do I fix that? How do I fix the original item in the original bucket? Well, we already know how to do that. We have to use an ampersand to work on the buckets in place, and we have to use an ampersand to work on the items in place. It's kind of weird because we're using the ampersand in two ways here. One is I need to get the bucket in place. I need to get the item in the bucket in place, and then I need a pointer to the item that's in the in place bucket in place. A little bit wild. Let's see if we're getting any closer. Let's see, where am I off? There's a space. So as far as I can tell, items in, everything looks good except for strawberry. Should have a space in front of it. So grapefruit should have a space in front of it. And then I can see now by looking at the, this is what it was supposed to be. I can see that there's a space in front of grapefruit, strawberry, and that there's two in front of blueberry. So I think I'm supposed to put a space here after the end of each counterpart of each entry. So let's see if that fixes it. Only take 5 minutes to build. So Magenta's asking, is that problem that I'm having because the strings are longer? So it is because the strings are longer, but also those long strings actually kind of exposed to me that the unit test was expecting that space after the closing parenthesis. So the longer strings did kind of erase the space, but also the unit test was telling me there's supposed to be a space there. So I just figured, well, the only way for me to pull that off. Oh, no, I see something else. Now I see something else. So yeah, it was the long string helped me figure out that it looks like spaces were supposed to be after the parenthesis. But now I'm noticing that there's supposed to be a space before the parenthesis. Maybe it's the before that matters, and I think it's both. So I'm studying the expected, which is the second part, and I'm just seeing my apple is squished up against the 2 and theirs isn't. So I'm going to go fix that. Right here, my word apples was squished up. So I put that space, and then I saw a little bit earlier that perhaps there was supposed to be a space after that parenthesis as well, in addition to the size 10 column width. So this one is the unit test kind of being a pain and making me drill down in pretty hard to figure out what the differences are. All right, that was the difference. So I wanted you to see also just kind of my process of using the unit test to hone in on what's wrong. And in that case, I could just look and say, oh, it expected there to be a space there, but I don't have one, so I'll go put one and see what happens. All right, so now I'm passing all of them. I will screen all of this. All of the code that I wrote is in this file, so I will, it's 11:23 for about 2 minutes. I'll just put these back on the screen. So there's insert. Not too bad except for the get check and the adjustment of the counter. I can move this down and say also there's the remove. So the whole trick to remove is to make sure that you are working on the buckets in place if you write it this way. And then I use the fact that vectors, which is what buckets are, you can target and erase individual items from out in the middle of them. Okay, there's remove. Next is, we'll do get and size. So get, I had to go back, and I was pretty sure I was going to have to, but I wanted you to kind of see it highlighted for you. I realized in my unit testing that the counters weren't getting updated, so I had to kind of backtrack. So when are the counters supposed to be updated? It's right here on the insert using that pointer that I got from get. So in sort of backtracing, I realized, oh, the get may not be giving me what I needed to alter the item in place. So I kept track of that because I was pretty sure that was going to happen. And then I realized, oh, I probably need to get the bucket in place and the item in place so that I can return a pointer that allows someone to edit the thing in place. So that one's one of the more difficult ones. The size of the hash table function is also on the screen. So there is not a matter of how big is the array, how many buckets are there, but actually how many items if you total up all of the buckets. So you take the size of each bucket, which is the number of items in each bucket. You sum that up. That gives you how many items are actually being stored in total in the hash table, all of its buckets. All right, there's those two. Here's the public hashing function, which is just returning the result of the private hashing function on the item's contents. And then the toString, which I don't need this little template anymore, so I'm going to clear it off. The toString function, which I had to experiment with in the unit test to get it dialed in to precisely the formatting that the unit test wanted. So I had to follow the instructions and use that set width to 10. But then even after I did that, I noticed that it needed spaces both before, one extra space before and one extra space after the parenthesis around that counter. And then the last one is the private hashing function, which we did in the other example, which is summing up the characters in the parameter string and then using mod to carve it down to the desired range of possible index values, hashing values. Okay, and that's it. Let me run it with the full glory of all of it passing. So I wanted to just point out to you, so in this output here, the reason why there's a 2 next to Apple is because someone tried to insert Apple twice into the hash table. This is a similar idea to what we did on Project 4. So instead of putting Apple in there twice, what we did is we have a counter for how many times was Apple encountered to count the encounters. So Apple, someone tried to insert Apple twice. Orange only once, grapefruit once, grape twice. 2 inserts were attempted on grape. So we inserted it once and then incremented the counter the second time and so on. And then I don't think there's anything else going on. Yeah, the rest of them are just successes. Okay, so I didn't know that I was going to use the full time, but I did. So sorry about that if you didn't want that. But there's some notes on the screen. So just some ideas that you might take if you're looking for a place where you might either grow or just continue to practice. Or in some way learn new things or get better and more confident at this stuff. So there are more data structures. If you're going on to a PNA 3 type of class, there are more data structures to come. They will take some PNA 3 classes, will take your binary search tree and basically figure out how do I keep it balanced so it has as much as possible the same amount on every level of the tree. So there are algorithms that balance trees, and that's what red, black, and AVL trees are referring to as balancing algorithms. There's also M-way trees, and those are trees that have multiple, that's what the M means, multiple way trees, where a node can have more than 2 children. You have graphs, which is another kind of algorithm. Google Maps uses graphs a lot, and a lot of network hardware uses graphs to route traffic. So that's another data structure you could explore. If you're looking for problems, there's Advent of Code, which I've advocated for because I like the problems in there generally. Project Euler and HackerRank also have problems you can practice on. You could press yourself to learn languages. One of the sort of newer imperative languages like Go or Rust. The older imperative language, which is C, which is I still think a good language to know. Or you might try a functional language, which will compel you to learn a completely different way of thinking about programming. It uses a lot of recursion, so functional programming is a good place to practice your powers of recursive thought. Anyway, there's my ideas. It is now exactly 11:30, so I'm going to sign off here. Thanks for the work you've done this semester. One more lab due before Sunday if you're going to do it. Discussion due before Sunday. So I'll get up early on Monday morning next week and finish my grading, and then I will call it quits as well. Other than that, I wish you the best of luck. I am still available this week by Canvas Inbox, office hours, and in Piazza. We'll still be using Piazza, so all the channels are still open until the end of this week. Thank you, Magenta and Edcast. I appreciate that. Yeah, so for those of you who don't know, I'm retiring on December 17th officially. But I'll be getting my grading done before I actually call it done. Thank you, Robo. Very much appreciate it, you guys. So you're in good hands. We've got some good people here at Butte College if you're sticking around. If not, there are good people at Chico State. So announce yourself, get to know people, be confident. You have worked to acquire a set of skills that is hard to acquire. So be confident. I would always tell people, be honest about what you don't know, but be confident in your ability to learn how to do it. Okay. Anyway, take care. Have a great holiday. And best of luck with whatever it is that you do going forward.